inviting me to speak here. So I hope the transmission is going to be stable. So I will talk about joint work with Shuang Miao and Wuhan and Wilhelm Schlag from Yale. Okay, so I will talk about wave maps, specifically critical wave maps. But so let me quickly give the background and then dive into more technical things. So a wave map describes maps from basically a Lorentzian manifold, in my case Minkowski space, into a manifold, and the manifold is going to be very specific. It's just going to be the sphere, but generally it's going to be a Riemannian manifold, which one can visualize as isometrically embedded in some ambient Euclidean space. Minkowski space for me is always RK plus 1 with -1 for the time direction and +1 for the remaining directions. And a wave map is then a solution to the following system of nonlinear wave equations, which we can then cast in terms of the ambient coordinates of R capital N. So this really encodes the property that box U is perpendicular to the tangent space of M at U, but one can express this in terms of the second fundamental form here, as I, J, K are the coefficients of the second fundamental form. And so you get this system of semi-linear wave equations here. So I always tacitly sum over space-time indices. There is the standard raising, lowering conventions are in use. And box is the Dallon-Burschen in this form. Now I'm particularly interested in the case when k equals 2. So R2 plus 1 is my Minkowski space, and target is S2, visualized as standard in the standard way as submanifold of R3. And the reason for that is because when k equals 2, the problem becomes energy critical. So a standard fact is that this is a Hamiltonian equation, so it has a conserved energy. And remarkably, because of this very special structure in the nonlinearity here, actually, so one can actually show, and I will talk more about this later on, that this problem is strongly locally well-posed all the way up to an epsilon of the energy itself. And this is going to play an important role because it sort of it seems to enable sort of a large class of interesting solutions for this problem, whose properties one can study. And these solutions, they don't come up in every model, but they come up in these kind of special Hamiltonian wave equations, it seems like, and also Schrödinger equations. So I will, of course, introduce these kind of special solutions later on, but for now, it's just important to know that this energy critical wave maps equation has a lot of remarkable properties, and amongst them is the fact that you have this very strong local well-posedness property, which is much better than for more generic equations. Target S2 is important because there are lots of interesting special solutions, so-called static time-independent solutions in this case, and they simply correspond to harmonic maps here, because wave maps is simply the wave analog of the harmonic map equation. And these special solutions, these harmonic maps, static solutions of this problem, play a very important role in that they generate certain non-static dynamics, which are interesting to study, and that's really what this talk is going to be about. Now, okay, so this wave maps model, if with S2 target, of course, it becomes simpler. So you get this sort of innocuous looking right-hand side. But the fact that there are these derivatives in there still causes some very, very serious technical difficulties in this kind of problem. So this is much harder to study in general than equations without derivatives. So I already said that there is this special structure here, the special arrangement of time. What's that? There's a special arrangement of time and spatial derivatives in here, and that's a so-called null structure. And this is a very strong null structure. There are different types of null structures, and this is kind of the strongest null structure, so-called Q0 null structure. And these kind of expressions, the importance they have, this is a long story. In the 80s, Christodoulou and Kleinemann revealed that for three-dimensional wave equations, for example, these kind of null structures are very helpful in establishing global existence of small solutions. For example, So you're willing to put as many derivatives and weights as you want on the initial data, but they should just be non-zero. And even that question of seeing when do you have a global and time solution is highly non-trivial in 3 dimensions. And null structures are seen to help you in this. And if you don't have a null structure, then you may have examples where you have finite time blow up for any non-zero initial data. So this was the first instance where these null structures came in. And so why is this not? Okay, good. And later in the 90s, or in a second phase, Kleinemann and Macedon realized that these null structures, they are also important for the question of local well-posedness. And they showed that in fact, equations with this null structure, for example, in 3 dimensions, again, in particular in low dimensions, this issue comes up. You can get very good results. You can almost go all the way to the scaling regularity. Whereas certain equations without null structure, you can give counterexamples to this. So the famous result by Kleinemann and Macedon was that if you have a system of wavemaps type, it doesn't have to be exactly the wavemaps equation. So the only thing that's important here is that you have the Q0 null structure, but the Sij(k) could be any kind of smooth coefficients. So if you have this, then you can always show strong local well-posedness all the way up to the hn/2 plus epsilon level. And hn/2 is exactly the scaling critical level, but below which you expect this thing to be ill-posed, of course. So this was then generalized to the case n larger or equal than 2, and in particular for the energy critical wavemaps equation, which is of interest to me in my talk. These results imply that you have this strong local well-posedness all the way up to an epsilon of H1. And if you compare this with another equation without this nice structure, such as Boxius ut squared, then in 3 dimensions, for example, one can show that this is ill-posed below H2. So you're half a derivative away from the optimal level of that you could expect to have strong local well-posedness. Okay, so this is important. The fact that you have this a good theory for fairly rough initial data for what I will talk about in the sequel. Okay, all right. So now, well, how does one show these sort of things? I don't want to go into details here because this is only very tangentially related to what I will talk about in the sequel. But so they are based on so-called XSB type space or HS delta spaces. So they're like Sobolev spaces, but with a symbol which is adjusted to the wave equation instead of the Laplace operator, the D'Alembert. And I mean, at this stage, it seems like we don't have a very good theory analogous to this for backgrounds which are very far away from the flat background. There are certain moves, there are certain results by Tataru and his school that look at more general backgrounds. But if you have a background which is wildly different, such as in the applications that I will talk about later, where you have blow-up solutions, it seems like we are lacking a good concept of XSB space at this time. So this is something that would be desirable. But part of my talk is going to explain how you can sort of come up with substitutes for this to deal with situations where in spirit you should have an XSB type theory available. Okay, so why do people care about these rough solutions to begin with? So of course, the original motivation that powered certainly a large part of the Kleinemann-Macedon machinery was to get as close as possible to the conserved energy, because I mean, there people were trying to establish the large data global existence result, which you have, for example, when your target is nice enough, such as a hyperbolic plane, then for any kind of nice enough initial data, you have global solutions for critical wave maps. And it was understood that to approach this problem, you had to have sort of a well-posedness theory that was basically at the level of the conserved quantity, which is the energy for the critical problem. However, so for my talk, the motivation is somewhat different in the sense that so what we now understand somewhat better, and there are more and more examples of this, is that to fully understand the richness of dynamics of problems like the critical wave maps, you have to understand the role of the topology plays in this. And depending on what kind of topology you impose, you may get very different types of dynamics, in particular, very different types of singular dynamics. And sort of a very striking recent phenomenon of this is the work by El-Guindi on Euler equations, which showed that you can have certain symmetry reductions of Euler equations where you may have some topologies in which you can construct finite time blow-up solutions, but if you put more restrictive topologies such as C infinity or an analytic data or something, then you would lose these kind of dynamics. And I mean, for my talk, so the interest that we had was, well, trying to find sort of very stable dynamics. And it turns out that in this, by enlarging the topology and looking at a sort of very general class of initial data, we were able to find solutions that are indeed very, very stable under quite general perturbations. And so it seems to be sort of nice to look not just at C infinity data, but sort of general data to get a more complete picture. But so to get this discussion more concrete, so okay, so what is known about critical wave maps with target S2? Well, there's the kind of the most basic fundamental result is due to Sterbens and Tataru from 2009, the threshold theorem, which shows that if you look at initial data whose energy is strictly less than that of the minimum energy non-trivial static solution, the stereographic projection harmonic map in this case, then your solutions will scatter. So there's no interesting dynamics taking place. So if you want to study something interesting, you have to sort of go beyond. You have to look at energies that are at least as large as that of Q, or actually strictly larger. And so the question that we were interested in was to understand, are there non-trivial, non-scattering, stable dynamics beyond this threshold? And by stability here, I really mean stable beyond a symmetry reduction, sort of really looking at very general classes of perturbations. And is there some sort of machinery one can develop to answer and think about these questions in sort of a systematic and general way? And so we came, of course, from this kind of Fourier approach, the XSB spaces and so on. And so therefore the story that I will try to tell here is very much Fourier based, which is very much complementary to the school, let's say, that Miao and Raphael have developed, which is very much based in physical space. So, all right. So the first thing is you need to have sort of a candidate of solutions that you want to, whose stability you're trying to understand. And in particular, I want to look at blow-up solutions. So what people did for a long time now, because the problem is so hard, they looked at a suitable symmetry reduction, and so-called co-rotational solutions were studied both theoretically and numerically. So what is a co-rotational wave map? In terms of the polar coordinates, it's a wave map which can be written in this form. So you can purely encode this problem in terms of the polar angle as a function of time and the radial variable r in R2. So this is the k=1 case. Then you can generalize to higher co-rotation indices, of course. And then it turns out that the wave equation is vastly simplified here. You magically get rid of the derivatives on the right-hand side, and it truly becomes a semilinear type equation, really in 1+1 dimensions. And well, so for example, the minimal energy harmonic map, the stereographic projection is an example, which would correspond to U of t and r being equal to Q of r, which is 2 times arctangent r. And so it's been known since work by Christodoulou and Struve and also lots of numerical work that for this model here, these static solutions that I've displayed here, they play a very important role in the formation of singularities. So if there are singularities, they have to manifest themselves in terms of a bubbling off scenario where you bubble off dynamically such a solution Q up to a radiation part. So this was known. And so people try to realize such solutions. And one way that one could construct such solutions is the one that's due to Schlag-Tataru and myself from 2006. And it said the following, that somewhat surprisingly, so here you prescribe the dynamics of the bubbling off. So you prescribe this function lambda of t, which is t to the -1 minus nu. And it turned out at the end of the day that all you need is that nu be strictly positive. So it has to be strictly slower than self-similar. It has to be a type 2 type blow up. So if you prescribe this scaling law, then for any such nu, you can, on a suitably small time interval, starting from 0 to t0, 0 is the time of the singularity here, you can construct blow-up solutions of that form, Q, a rescaled ground state, plus a radiation term. But what was slightly strange about, well, two things. First of all, that there is a continuum of such solutions. And the second thing is that they're never of C infinity before blow up. So these solutions are strictly rougher. They're only of regularity H1 plus nu, slightly less than H1 plus nu. You can make them as regular as you want. If you choose nu large, you can choose nu arbitrarily large. But you will never be able to make these things C infinity. So if you really want C infinity data, it seems like things are much more rigid and quantized in a way. There's no such continuum. So how could one build this? So the actual structure of this epsilon will play a role in my the continuation of my talk. So it's somewhat technical. The way that one builds such solutions is really in two steps. So in the first step, you add a first correction, which is highly structured. So you really can reveal the exact algebraic structure of the corrections that you add at each step. And that way you can, after finitely many corrections, you can add as many corrections as you want. You can produce a solution, which is not quite a solution, it's an approximate solution, but the error can be made as small as you want, in the sense that it decays, the error can make to decay like t to a power 1000 as you approach the actual blow up time. But you will, it seems like you can never get the exact solution that way. So then to get the exact solution, in a second step, you add a final correction. And this final correction is obtained by solving suitable wave equation using parametrices and estimates, losing the fine structure to some extent, but being able to then finish the thing off to get an actual solution. So very important that there is this a rough part, which is responsible for this H1 plus nu minus regularity, which you can actually make very explicit. And it manifests itself in terms of a shock that these solutions experience on the light cone, which is centered at the singularity. And then there is a better part, which is smoother and less structured and decays very fast as you approach the blow up. So how are these things actually constructed? So the rough part, which gives you the approximate solution, is, as I said, so you add finitely many corrections to get a good approximate solution. How do you obtain these corrections? Let's assume that it's an inductive process. Let's assume that you have accomplished stage k minus 1. Is an approximate solution. It generates an error ek minus 1, say. Then if you wanted to complete this to an exact solution, you would have to solve the following type of wave equation, where you simply linearize, you simply perturb around the uk minus 1 approximate solution. The uk minus 1 being the sum of the bulk part plus the first k minus 1 corrections that you've added. And of course, it's again not clear really how to do this, because it's a wave equation and there's a potential term here. And the potential term, because it contains in particular the rescaled bulk part, is time dependent. So you have a wave equation with a time dependent potential term, and the scaling of course makes this thing shrink to a point. So it's very it's a complicated kind of thing, but there is sort of an ad hoc way to make this work. So basically the problem is that this is a wave equation here, and there are two ways in which you can sort of simplify this. One is that you throw away the time derivative. Then, because we are in a co-rotational setting, there's only one variable left. This becomes sort of an elliptic equation, and this you can solve by simple variation of constants formula, and you get, of course, an explicit solution in principle of this kind of elliptic problem here. The second one is a little harder. So here you don't throw away the time derivatives, but you simplify the potential term, let's say. So you only take the leading part, you disregard the corrections that you've already added. So this gives you a sort of fairly simple wave type equation, but it's still a wave equation. And so how do you solve this sort of wave equation with a potential term that's time dependent? And there sort of the key insight is that you make a suitable algebraic ansatz. So you look for a solution of this, which is a function of this variable a, which is r divided by t, the self-similar variable, divided by a suitable power of lambda times t. So lambda, remember, is t to the minus 1 minus nu. So lambda times t is t to the minus nu. So you make this algebraic ansatz, and the miracle that happens is that as you then write down the equation for q that you obtain, the wave equation transforms into an ODE, which, however, is singular at the light cone. And if you then write down a fundamental system for this left-hand side near the light cone, then you obtain these expressions 1 minus a to some power depending on nu plus 1/2. So this is the important thing, that of course, if this is exactly 1/2, then you just fail to be in H1 near the light cone, and because you add nu, so you're a little bit above H1. This is the reason why this is an H1 plus. And of course, away from the light cone, these types of solutions are C infinity, right? So it's only at the light cone that you experience a cusp, and this cusp becomes stronger and stronger the smaller you choose nu. And then one can make this very explicit. So you get this type of symbolic expansion of this shock that these solutions experience at the light cone. Okay, so this is the first stage. And then you have to complete this approximate solution after you have added capital N of these corrections. You're trying to complete this to an exact solution. So the error that you're making after stage capital N, you can make this decay very fast in terms of time t as you approach blow up time. And so then in the end, you still have to solve a wave equation. And of course, now you have to do something different, but you can take advantage of the fact that the error that you're left at this stage is extremely small. I mean, decays extremely fast with respect to time. And so in the second stage, this is where the Fourier methods really come in that we used. And these Fourier methods, they will be very important also in the sequel for what I will talk about. And it seems they have a lot of potential to elaborate on further and to apply to many different contexts as well. So basically the point is to kind of develop these Fourier methods in sort of a very modular fashion and to point out certain key aspects which then get repeated in many other situations. So what is the basic object? Of course, it's the linearization around this Q, let's say in its time independent realization, just Q of R being 2 times arctangent R. And then the linearization that you obtain is this elliptic operator here. And then one can develop its spectral theory. The unpleasant thing about this operator is that it's singular at the origin. So it doesn't strictly fall exactly within Weil theory, but there are extensions of this, and due to Gestesi-Zinchenko in particular. And this allowed us, basically furnishes you with in this case, a fairly ready-made Fourier theory. So in particular, you can write down a Fourier basis, which gives then a Fourier representation of functions. And the important thing here is, so there are basically, for these Fourier bases, there are always 2 regimes that you see. As long as R is sufficiently small, more precisely, it's less than the so-called turning point here, this Fourier basis behaves in a non-oscillatory fashion, and you can write down a Taylor type expansion. And as R gets slightly larger, more precisely R times psi to the 1/2 is larger than 1, then these eigenbases start to behave in an oscillatory fashion, and you have a Hankel expansion for these functions. And so this is going to be important also for later on, because there will be sort of an infinite sequence of operators where we'll have to exhibit similar types of eigenbases. Anyway, so then one can also calculate the corresponding spectral measure. Of course, these eigenbases are not uniquely determined. You could always multiply this with some kind of power, some function of psi, and then you would have to adjust the spectral measure correspondingly. So we use this kind of realization that's written down here, and then you can compute what the spectral measure is. So our eigenbasis has the property that as psi goes to 0, you're approaching this function R divided by 1 plus R squared, which has a very important significance for this problem. It's the resonance. It's sort of generalized root mode for the linearization of our problem. And this is, of course, linked to the symmetries, the scaling symmetry of the problem. Okay, so then, all right, now I would like to use these Fourier methods to solve the corresponding wave equation. The problem is that the operator, really the linearization is time dependent that I have. There's a time dependent potential term, and to get rid of this time dependence, I make sort of naively maybe a change of coordinates. You introduce this variable capital R, which is lambda of t times r, and a new time variable tau. And that way you get rid of the time dependence in the elliptic part. But of course, for the time derivatives, you have to pay a price. You introduce these dilation type operators here. So that causes a lot of complications, of course. You get these lambda tau divided by lambda times r dr type terms in these generalized time derivatives here. And this is the kind of wave equation that we are now trying to solve. Now, if you're trying to do this on the Fourier side, then, so again, ideally, you would like to translate r dr to minus 2 psi d psi, which in the flat context works beautifully, but I mean, here it doesn't. You will make an error. And this error is the so-called transference operator that comes in here. And this transference operator, it has two parts. There is a part on the diagonal, and then there is an off-diagonal part, which is a Hilbert, is an operator a bit like a Hilbert transform here, a singular integral operator, is a non-local operator here. And of course, the properties of this non-local operator play a very important role. One very nice thing about it is that it has a smoothing property. So if you have a function f which decays in a certain way at infinity for when psi becomes large, then k0f decays half a power faster. And so on the physical side, this would mean it's a smoothing effect that this operator has. Okay, so so then there's also the spectral measure, and the spectral measure here reflects the presence of this resonance at the origin, and this means it's a singular function. It's 1 over xi times log square xi. It's just barely in L1. And the singularity is causing headaches when you try to write down a wave parametrix, so the solution of the wave equation in terms of the Fourier variables. The spectral measure is going to show up in there. And the fact that it is singular at the origin means that you will have trouble when you try to obtain temporal decay for certain, for the solution of the inhomogeneous or homogeneous problem. And this is something which you have to circumvent. And it's something that we will get back to in the sequel. Okay. So the singular spectral measure you might think that this is causing difficulties, but it turns out that the procedure in this old work of Schlag-Tataru myself, it was so robust that even with all this, one could sort of naively translate things to the Fourier side, and taking advantage of the very rapid decay of the error after this that's generated by this approximate solution, one could iterate everything away. So one could even be very crude and not pay much attention what you actually move to the right-hand side and what you incorporate into the wave operator in the Fourier formulation on the left-hand side. One could be very crude. So for example, what we did is we put everything that was due to the transference operator onto the right-hand side, even including the diagonal part in the transference operator, which in a way is maybe it's more natural to put this on the left-hand side and include that into your actual wave operator here. But nonetheless, everything worked out. However, there were some technical issues that would make this kind of approach, if you try to understand the stability of these solutions and not just construct one example, but if you try to actually perturb things a bit, then one had to work much more carefully somehow. And that's why, when we wrote this paper 14 years ago, the stability of these solutions was completely unclear. So we at first conjectured that they might be stable along a very high codimensional manifold, but in general, they might be unstable. And it turns out actually they're, at least when nu is very small, when your scaling parameter is very close to the self-similar one, then these solutions turn out to be actually highly stable and even rigid, okay? But you have to work more carefully to get this. Okay, so how can one approach the stability of these solutions in the co-rotational setting? Okay, so I'm still just co-rotational here. And again, so from now on, one has to choose nu very small, for reasons that will become apparent. So it's actually very natural, and also it corresponds to what one observes in numerics, that you will not, so the stable solutions are always very close, that scaling parameter is very close to the self-similar rate in these. So the result that we proved in 2018 Miao and myself, was that if you choose nu small enough, in the co-rotational setting everything, and you pick a perturbation of these KST solutions, whatever, from 2006, the perturbation, so the increment that you add to the initial data has to be smooth enough and small enough, then the perturbed data result again in a blow-up solution, which blows up in the same space-time location and with the same scaling law. So it's extremely rigid, this kind of thing. Now you can say this seems strange, because how could you even blow up in the same space-time location? Because after all, you can translate these things around, so this doesn't make any sense. But the point is, if you take one of these KST solutions and translate it around, and you compare the data of the translated solution to the data of the original solution at fixed time, then you will see that the difference, the increments that you've added, they're rough. They're only of regularity h1 plus nu. And the crucial thing here is that the increments have to be much smoother. They have to be of regularity h4 and h3. So there is no contradiction from this. Okay. So, all right. So there's a rigidity in these solutions even. Why do you have to choose nu very small? Well, the reason is because if you go into this new time coordinate tau, and you express lambda in terms of this new time coordinate, then it becomes a very large power of tau, tau to the 1 plus nu to the minus 1. So it grows very fast in this variable. And it turns out that this fast growth can be parlayed into very good decay estimates on the Fourier side for the wave parametrics, if you use suitable weighted spaces to control your solution. And this is why you have to choose nu small. Now, okay, so to get this type of result, like I said, one has to be very careful how one translates things to the Fourier side. In particular, one has to be careful with this transference operator, which translates RDR into CDC plus something. And also one has to get rid of this singular spectral measure. And there one uses this supersymmetric trick that was introduced originally by Gustafsson, Kang, Tsai, but I think it goes back to physics literature. It was used by Raphael Rodniansky, later by Bejenaru, Tataru, and myself. And so this trick basically exploits a remarkable product structure in the linearization around the ground state. And this is something which is actually not just in the co-rotational setting. So this is much more, it's something which is much more general and which will recur later on. And finally, you also take advantage of the fact that in the co-rotational setting, the equation is really sort of elementary in the sense that there are no derivatives. And so if you think, I mean, this is basically like a pure power nonlinearity. And if you combine that with the Duhamel propagator, you gain regularity. So it has a smoothing type property, which is very important. So, all right. Now, so supersymmetry, as I mentioned, that there is this remarkable product structure. How does this come about? So here one introduces this operator script D, and it has its adjoint D star here. And then the remarkable thing is that D kills the resonance. And moreover, the Hamiltonian, so the operator L from before, it factorizes as D star times D. And so now what one does is one basically, instead of working at the level of the original perturbation epsilon, one works at the level of the derivative of epsilon. One looks at d epsilon. Then of course one has to go back to epsilon. So one has to write down an inverse for this, which one can do in the form that I wrote down here. And then of course there is 1 degree of freedom here. So you have to add a multiple of the resonance to reconstruct the original epsilon. And to actually read off the C of tau, it suffices to look at the behavior near the origin of this, and you can read off what C of tau has to do. You can, from the wave equation, you can infer an ODE, which governs the evolution of C of tau. Of course, that depends on the behavior of the epsilon. And then one observes that d epsilon solves itself a wave equation, which has better properties. So the elliptic operator that comes up in the equation for d epsilon doesn't have a resonance at the origin anymore, and its spectral measure is less singular. And so this turns out to be the right quantity to work with. So to control your epsilon, you have to control a pair consisting of d epsilon and of the variable C of tau. So then what are the steps? So these, I just write down the steps, and this is kind of an outline, which is then also being used in a much more general context later on when I look at the non-co-rotational problem. So first you of course have to translate the equation for d epsilon to the Fourier side. You have to derive the equation for d epsilon, which is a computation. You have to treat the Fourier equation, the equation on the Fourier side, by introducing a suitable functional framework. And these are certain weighted spaces, but L2 based spaces. There is a complication if you work on the Fourier side, because as you remember, there are terms generated by the transference operator. There are these non-local terms, which are linear in X. And so the equation on the Fourier side is really becomes an integral differential equation. And it's not so clear at first sight how to solve this, but there is an iterative procedure which allows you to do this by exploiting the remarkable properties of the transference operator. And then finally, you also have to analyze the ODE, which you get for the unstable, for the multiple of the resonance. And of course, I mean, this cannot be done in one step. So sometimes one has to go several steps into the iteration to get smallness in some of these things. So it's fairly delicate. Now, of course, there is the shock on the light cone. So you can ask, does this shock on the light cone cause any difficulties in this? And it turns out here it doesn't cause difficulties because of the smoothing property of the nonlinearity in the co-rotational setting, that you don't have derivatives. So this means, again, so if, of course, there are interaction terms of the perturbation and the shock, but they interact, there's no derivatives, and then you apply the Duhamel parametrics, and then you get something which is 1 degree smoother than the original shock. And that is enough to still get, to make everything work and to not get difficulties here. So this is kind of the roadmap, and we were trying to now establish, use this kind of roadmap to also see what happens in the non-co-rotational case, okay? Okay, so very quickly here, so this is the equation that you get when you apply D to your equation. It's a bit of a mess. You generate additional terms because you have to commute D past these time dilation type operators. So you get some new linear terms here, but they come with weights. They're both temporally decaying, and they're decaying in R. And that turns out to be enough to iterate these away, so you don't have to worry about them. And most importantly, the linear operator that comes up here, this L tilde, is now better because in it you have done the supersymmetric trick. You have switched the factors in the original factorization of L, and therefore you have a much better spectral theory for this L tilde. Now, do you have to do the whole work again that you did to get the eigenfunctions for the original L? No, there's a simple way to translate. Once you have eigenfunctions at the level of L, you get the eigenfunctions at the level of the eigenbases at the level of the supersymmetric partner by means of this simple formula here. And then you also know exactly what the spectral measure does. And you see the spectral measure is now much less singular. It's only like log to the -2 psi, so it even vanishes at the origin. And so then you have a corresponding Fourier representation, and you work with this. You again have the issue that you have to translate RdR to the Fourier side. So you have a transference operator. But this time, someone is being very careful what one does with this transference operator. So one introduces, instead of the original d tau -2 lambda tau over lambda psi d psi, which was used in the 2006 work, you include an extra term here in this. And that way you include all the diagonal terms generated by the transference operator as well. And on the right-hand side, you only have non-local terms left due to the transference operator, and these turn out to be good. And then the equation on the Fourier side becomes this here. And so now it turns out that for the left-hand side, for this type of wave operator, there is a very explicit parametrics one can write down. And for the right-hand side, okay, so these script R terms due to the transference operator, so they are weighted linear terms, but it turns out these can all be iterated away. Okay, so they don't really cause problems, although it's a little bit technical. Okay. So the left-hand side, I said, so that's nice. There's a very nice formula which you have, so an explicit solution here. And then you can work, and this is very important. You have to use the right weighted spaces to handle this. So you see there is a weight which vanishes at the origin, sort of to counteract the issue in some way of resonance. And also you have to have enough decay at infinity. So you need to have, so this Japanese bracket, of course, is square root of 1 plus psi squared. So it has to be regular enough that you get enough decay. And then if you apply the wave parametrics that I wrote, then you get these types of bounds. And remember, lambda of tau is like tau to the 1 plus nu minus 1. So these kind of factors that are come out here, they give very rapid decay of these norms with respect to time. And this is what helps you to control, you know, you get this decay kind of for free in this, just from the scaling. Similarly, you have to make sure that you control epsilon in terms of these norms. So you need these type of Sobolev type estimates here. Okay, but so this is kind of the spirit of the co-rotational kind of thing. Now, well, how do you now try to apply these sort of methods? What kind of difficulties do you encounter when you go beyond co-rotational? Well, the first thing is, of course, you need to have sort of a good setup, the right coordinates, because this problem becomes vastly more complicated. So the problem now is you start with the phi, which is this KST type solution that I was talking about, and you add a general perturbation. And the framework that we use is basically coming in part from work by Davila, Del Pino, and Wei, where they express the perturbation in terms of this frame here. This is, of course, a frame which is adjusted to describe the tangent space at phi, right, around the point of your unperturbed solution here. And so what you do is you make an ansatz for the perturbed solution, which is the sum of phi, a part which lives in the tangent space at phi, and I express that as a linear combination of this E1 and E2 frame. And then, of course, because that takes you outside of the sphere, you have to correct for this to go back into the sphere. That's why you have to add this correction Q. And of course, you define Q such that Q is actually parallel to phi. So this then uniquely gives the relation between psi and these functions phi1 and phi2, and you can derive a system of wave equations for these. And it turns out that if you do that, then that's not quite the nicest way of doing it. So you go into complex variables, and you introduce these phi1 plus minus I phi2, and that way, of course, you get a matrix valued linearization now around this solution. But that way, if you go into this representation, then this matrix, actually the potential term becomes diagonalized. And so in the end, you get sort of an infinite family of analogous linearizations to what we had before, as if you actually use a Fourier representation with respect to the angular variable. So that's what we do next. We expand these epsilon 1, 2 in terms of a Fourier series with respect to the angle theta. And then for each mode n, you get, I mean, there's plus and minus sign here, right? But for each mode, you get a kind of wave equation like this, which is now, again, very similar to what we had in the co-rotational case. You have the time derivatives here. But of course, now you have different operators here, hn plus minus. And the right-hand side, I'm not even trying to write down. It's extremely complicated. However, so the most fundamental difference that you experience with the right-hand side is that you have derivative terms. You have now null structures that come up in here. And these null structures, of course, they cause serious complications because of the shock on the light cone, right? So this is where now we have to work much, much harder to control the contribution of the shock on the light cone. Nonetheless, so the theorem that we have is the following. So you take one of these KST blowups for nu small enough, and you take an arbitrary perturbation of the data. There are some technical restrictions. So the perturbation has to be smooth enough. Let's say we put H100. And also there is a very technical restriction we put, which is not really essential, that it is supported strictly inside the light cone, which is centered at the singularity. There's no symmetry reduction there. And well, somebody should maybe mute. I don't know. So then the result says for these perturbed data, you again get a blow-up solution. And which can be written in this way. So you have the bulk part, then you have a radiation part, which asymptotically vanishes in the light cone. Of course, you always have to restrict yourself to the light cone to have this vanishing. It radiates outside of the light cone mostly. But what distinguishes this, of course, very much from the co-rotational case is that this time you do have to modulate. So you cannot get by without this. You have to use rotations. There are 3 rotations on the target which you can use. There is Lorentz transform, so you have 2 degrees of freedom in there, and you have the scaling freedom. These are all symmetries that do not displace the light cone. So the light cone stays fixed in this. Again, translations do not come up because the perturbations that you add are smooth. They're much smoother than the original blow-up solution. And so again, in particular, the blow-up locus remains the same. And these parameters alpha, beta, h, and so on, they all converge to terminal values. So they're alpha, beta, they would be small terminal values, and c is close to 1. Okay? So there's no crazy oscillations going on in these solutions. So they're actually very, very well behaved in that sense. So why do you have to modulate now? And really, again, it's a somewhat technical reason. It's because of the presence of these null forms in the nonlinearity which now come up, and the shock on the light cone, which produces terms that are too rough to get good time decay in the iterative scheme. And so you have to take advantage of the freedom to modulate, not so much on Q, but I mean, remember you're perturbing the original KST solutions. So what you take advantage of is the effect of the symmetries on the singular part of the KST solution. And you choose these modulations in such a way that the modulated singular part of the KST solution cancels against the singular terms that are generated by the interaction of the shock and the perturbation that you have. And this is what you have to use to actually to make the scheme converge at the end of the day. All right, so how does this work now in detail? So of course, so I say you do this Fourier expansion in angles, and then for each angular mode, angular frequency, you get an operator here. So you get these hn plus minus, and so there's n dependence. And now in principle, for n going to infinity, you need to develop the analog of the theory that was used in the co-rotational case. In particular, you want to have a good description of an eigenbasis. You need to describe the transference operators, and you need to have certain very detailed information about these transference operators. And you have to make sure that things don't diverge somehow in terms of n. So this is it's a very delicate type of issue. And what we use is really a theory that was developed by Donninger and Schlag and Staubach in the context of general relativity, actually, in the problem of stability of black holes. And it turns out that this kind of theory fits this kind of setting here like a glove. In particular, so one gets very nice, basically, I mean, roughly speaking, so I don't want to go too much into details here, but the idea is to kind of switch to a semi-classical variable h bar, which is like 1 over n, and to by passage to a suitable new system of coordinates to reduce the corresponding problem to a perturbation of an area equation for the generalized eigenbasis, and that way kind of compare things to area functions. Now, okay, so let me try to give just one aspect here that you have to do is when you for example look at the transference operator. So you need to translate RdR into xi d xi plus something. And the precise result is this. So looking at just the case of large angular momenta here, n. So you again get this family of transference operators. They all have the same, basically the same diagonal part. Of course, the spectral measure comes in here. The spectral measure is very well behaved. These spectral measures, they're all bounded functions. And as long as n is larger or equal than 2, and the rho of xi converges to a limiting point. And then there is this this non-local part in this spectral in this transference operator, and the non-local part again it allows for sort of a very precise description. So there's a kernel function f, and you can give very precise decay estimates near the origin and at infinity, as well as off diagonal kind of estimates which are kind of delicate. I mean, I haven't stated them here. And moreover, another aspect that's very important for us is certain differentiability properties of these kernels. In particular, we need the so-called trace differentiability properties of this. So we are not aware of anything like this in the literature, so we don't know. So this is part of what makes this very painstaking, is that everything has to be sort of developed by hand here, and there are sort of very subtle properties that come in. But so you can say, does one need all this? Well, on the one hand, we believe it's actually useful to have this information maybe for other problems, and second, we believe also that for the specific problem that we have to deal with, the description of the shock in particular, and the solution of the wave equation with this, we do need all of this information to actually get a good theory that substitutes for these XSB spaces that are not there. Anyway, so then what does one do? One has to introduce a suitable functional framework to run an iterative scheme. And it turns out that, so the right spaces that we use here, we have to use the right weights here. Now there is n, right? So h bar is 1 over n. So you have to include the right weights here to get a consistent framework here. So these kind of norms, they would be used to describe the Fourier transform of the perturbed solution in the interior of the light cone, where you're away from the shock. So this, of course, this corresponds to 5 over 2 weight, which means basically H5 regularity in terms of our coordinates that we have here. But this then needs to be complemented with a description of the solution near the light cone and where the shock happens. And there, to describe the shock, you will have less regularity, so you have less decay of your function in terms of psi. But on the flip side, you get more structure. So you get a algebraically very structured type of expression that gives you the shock. And then in the inside, you have this more smoother kind of functions, which are in this space as S0 H bar. Okay, and so then for each angular frequency n, you have to derive this wave equation on the Fourier side and use the kind of methods that we used in the co-rotational context to run an iterative scheme to control this. So this is now just for the exceptional, this is for the generic angular momenta when n is large. So when n is large or equal than 2 in absolute value. Then there is the issue, of course, that there are some exceptional angular momenta. And in this case, in our formulation, they correspond to 0 and plus minus 1. And this is where the symmetries of the problem manifest themselves. So for example, when you, here when you have the n equal plus 1 mode for h1 plus here, then you have an eigenfunction here, a 1 over 1 plus r squared with eigenvalue 0, right? So you have a root mode. And when you put n equal minus 1, then you will get a resonance. And then put n equal 0, of course, then there's also a resonance. So this is where the symmetries manifest themselves. And there you have to do something else. So there you cannot use the original formulation. You again have to use the supersymmetric trick. And it turns out that the supersymmetric factorization, this works for all n. So this is not just n equals 0, this works n equal plus 1, n equal minus 1, and so on. So here you can formally do the exact same procedure as you do in the n equals 0 case. You introduce the corresponding d plus and d minus operators, and you then work with the differentiated mode at n equal plus 1 or minus 1, plus the multiple of the root or resonant mode. And the description then, so you have to control both of these to control these exceptional angular modes. And so here, the problem again comes, now the serious problem comes up when you try to control the evolution of these multiples of the resonances and the root modes, specifically because of these, the derivative terms on the right-hand side in the shock, which gives certain source terms for these coefficients C plus minus and C0, which by contrast to what you get in the co-rotational case, here you would get something which would diverge, which is very badly behaved. And this is exactly why we have to use this modulation theory that I mentioned that comes up in the statement. So we have to make sure that by modulating on the singular part of the unperturbed solution, that we can cancel certain interactions of the radiation part and the rough part of the original unperturbed solution, to get good decay estimates for all these C plus minus and C0 coefficients. Okay, so this is the final thing. And so so in the end of, so what kind of estimates does one work with? Of course, it's very complicated to describe this whole the final result of this perturbation. You have for each angular frequency n, you have to describe the perturbation. So for as long as n is generic, meaning absolute value n is larger or equal than 2, it just suffices to describe basically the Fourier transform of your epsilon. But again, this description is also delicate because you have the shock, which is there. So there's sort of a smooth part of this description, and there's a structured singular part, which is too complicated for me to write down here. And then for the exceptional modes, you have to describe the evolution of the root and the resonance mode. And finally, you have, of course, also have to describe the evolution of the modulation parameters in this. So it's a large amount of information that you have to control, and also the kind of decay that you get for everything is actually, it's very delicate. So for example, these C0 and C plus minus 1 coefficients, they don't decay arbitrarily fast, but they only decay like t tau to the minus 2. So in the end, it just barely works out that everything closes. So it's a lot of work, but in principle, it results from combining the approach used for the co-rotational case, the right coordinate formulation of the problem, sort of inspired by the XSB type framework to handle this Q0 terms and the Q0 null forms and the influence of the shock, and then use this framework that Donninger, Schlag, and Staubach built to develop a spectral theory for this infinite family of operators that arise. So maybe it's okay if I close here.
Okay. Yeah.